This hit and run econometrics is called Where Does R Squared Come From? That very important measure that we've been looking at. R squared, it is a measure in the sense of how well the thing fits. And one answer is just this, the definition. What proportion of the variation is explained by the regression? The answer is R squared. That explained is in quotation marks because remember, we're not talking about causality here. It's just that they are moving along together. And in order to make some progress on this, we have to remember what EI is. It's the regression residual. And so that's equal to our actual Y minus what our regression line said that was going to be. See, it was an estimate of our YI. That would be YI hat. So that's just the definition of the residual. But if we wanted to isolate that yi by itself, we could rewrite it this way. No fancy algebra here. We could just take yi, and then we could take that negative yi, move it to the other side, and look what we would get. That yi is equal to yi hat plus ei. There we go. It's the estimate that we thought yi would be according to our regression line plus the residual, the part of that that we were unable to explain. And at this point, if we now subtract y bar, the mean of the dependent variable, from both sides, look what we get. We get that yi minus y bar, see that? We just took that side of the equation, subtracted off y bar, is equal to yi hat minus y bar plus, and then right here, the definition of the residual, which is the actual yi minus the fitted amount, that yi hat that the regression line had for us. So there's no fancy math going on here, but what we have done is to break down the variation of a yi from its mean y bar into two rather important components. That is, the total variation of an individual y from its mean, which is that much right there, is equal to two parts. The amount that is explained by the regression. See, our regression is going to run this, and it's going to show us how different from the mean any given yi hat is going to be. But it doesn't explain everything, and so there's also that amount due to the residual. This is the explained amount and the unexplained amount, and they have to add up to the total variation of that from its mean. And now we come to one of the most important diagrams in the class. And so in order to emphasize this, I want to draw it a little bigger than usual, and I also want to give you a reference, page 48 in the Studeman text, for you to go have a look and see this. I want this diagram to be sort of, impressed on you. So we're going to have y vertically and x horizontally as usual. And what we're going to have is a given xi, yi pair. Here's a value of the explanatory variable. And when it takes on this value, then what we observe is, as one of our data points, that we've got a yi way up there. And so this data point is where it all starts. Now, the dependent variable does have a mean called y bar. And here, this y bar, we're just going to draw a line across here to show how high y bar is. In this hit and run, I'm not going to go into detail about it, but if we were trying to figure out the salaries of all the different hitters on the New York Yankees roster, one very simple way of doing that would be just to say, well, let's take the average salary and just assume that everybody makes the average. And you would think, hey, that's crazy. You know, in history, the Yankees have had some of the great power hitters, some others that didn't hit the ball as much. So to say, let's all assume they make the average, that would be kind of a dumb model. But it is a dumb model that is very important from the viewpoint of reference. So we can draw just a line straight up from our xi to our yi. And notice that what we're trying to explain is the height of that point, because that's our actual yi. And we're trying to figure out how much is due to the influence of the x variable and how much else there is there. So when we have done this, we draw the regression line. And the regression line will use a whole bunch of data points, not just this one, but it comes as close as possible to as many points as possible, and that's going to be the regression line that you see right there. Well, the thing is that the total variation of this xi, yi point up here, the total variation of yi from its mean y bar is this vertical amount. See, this is how much it varies from its mean. And we can see that it's divided up into two amounts. There's this amount, this vertical height right here, which is the amount that is explained by the regression. Yeah, see, our regression line tells us, with an xi value this high, we kind of predict that your yi hat is going to be right there. So it is explained by the regression. And that is equal to yi hat minus y bar. And you can just see that's the vertical distance. It's a yi hat from right here on the regression line down to y bar. But that's not all, because there's the part that is not explained by the regression. See that? Not explained by the regression. We've done our regression and it fits this value right here, but hey, that point is still farther above the regression line, and that is actually going to be the residual, the EI. And you remember by definition, EI is equal to yi minus yi hat. So this is a very important diagram. It's just saying that our total variation of yi from its mean is equal to the part that's explained by the regression and the part that's not explained. They together have to add up to that total variation. Okay, let us have a look now at this total. In fact, let's just imagine taking those things and writing them with a slightly different kind of notation. And when we write them with a slightly different kind of notation, what we've got is this. That TSS equals ESS plus RSS. That the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. Now look what we did. We found that the total variation was equal to the explained, there's the explained plus the unexplained. But if we took those and squared them and summed them up across all our observations, this is what we would get. That the total sum of squares is equal to the explained sum minus the unexplained or residual sum of squares. And so this is, again, just that fundamental insight that the total is equal to the part we can explain and the part that we can't explain, all added together. And so if we take this equation right up here and divide through by the total sum of squares, hey, let's just do that right now. TSS right there, TSS right there, TSS right there. That becomes 1. See, that cancels out to 1. So 1 is equal to the explained sum of squares over the total sum of squares plus the residual sum of squares over the total sum of squares. And we've actually got R squared. Yeah, the thing we were looking at. Because R squared is equal to the explained sum of squares over the total sum of squares. The proportion of the variation explained. That's what we were looking for. It's the same as 1 minus the unexplained proportion of variation, which is RSS over TSS. And just a reminder there, R squared is the proportion of the variation explained. So what we do to get the concept of R squared is to divide up the variation into that we can explain and that we can't explain, and we just calculate the proportion of the variation explained. And that is the answer to the question, where does r squared come from?